Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 23, Correlation and Straight Line Regression, Part 4. We're finishing up Chapter 6 in this video. So we're actually going to do the example here as well. So the equality of two correlations, testing the equality of two correlations, and how large should R squared be in practice. Okay. So last time we talked about how to do a hypothesis test for rho equals 0 and for rho equal to some value that's not 0. And to do that, we needed the Fisher transformation. Very clever, not always the easiest to use in practice, so it's nice to have a computer. All right. So when we're testing for rho 1 equal to rho 2 using two independent samples, that's the key here. We're going to assume that the two samples have sizes n1 and n2, that they're independent, and we have correlation coefficients, sample correlation coefficients R1 and R2. We're then going to use Fisher's z-transform values, and those are independent as well. If R1 and R2, if they come from two independent samples, then their transformations are independent as well. You'll notice that the only thing included in here is R1, and the only thing included in here is R2, so it's not like we've changed the relationship between R1 and R2. So then we're calculating the Z1 and Z2, the Fisher transformations, and we subtract them. And then we take the square root of the sum of their standard deviations. And this is approximately a standard normal distribution, which is very nice. It's nice that it ends up in this form, which is very easy actually to remember if you had to remember it. But again, I'd write it on my formula sheet. Okay, so the single sample test of H naught, a rho 1, 2 equals rho 2, 3. So here is a null hypothesis that the correlation rho of 1, 2 of variable 1 with variable 2. Okay, so this 1, 2 means that we have, say, x1, x2. And here we have rho of 1, 3, so that would be x1 and x3. Instead of using x and y, we're using x1, x2, and x1, x3. Okay? So this is the correlation of variable 1 with variable 3. So we have a single sample instead of two independent samples like we had in the previous case. So we're going to assume that a single sample of n subjects is collected. So it's one sample. And we calculate these three correlation coefficients. And so, using theory, we can show that a large sample test statistic, so it has to be a larger sample size, for testing that rho 1, 2 is equal to rho 2, 3 is given by this very short little equation, right? Okay, so definitely something you'd want on your formula sheet. And this very nicely follows a standard normal distribution. So when we say that it follows a standard normal distribution, when we're testing a hypothesis, we use the same steps. We calculate the test statistic, right? We calculate that test statistic, and then we determine a rejection region. And once we determine the rejection region, if that criteria is met, we make a decision to reject or not reject the null, and then we do a conclusion. Okay? And the rejection region for the two-side case is going to be, in this case, that the absolute value of z is greater than z of 1 minus alpha over 2. So that's why we can do this hypothesis test. That's why there's not more information here, because we're assuming that you know how to do a hypothesis test and the steps and how to put this together. Okay, so now let's talk about a practical thing. How big should R squared be in practice? So if we want to use a straight line model for prediction, then R squared needs to be at least 0.5. that means it explains at least 50% of the total variation in the model. Of course, we'd like it to be higher. Some people want, zero point 0.6 or 0.75 or something like that, but you definitely want to have more than half of the variation explained by the model. Otherwise, you really don't want to do prediction. Okay. However, we can have statistical significance where r squared is kind of small. And the issue with this is that r squared it can be small due to the complexity of some variables like the BMI, body mass index. There's a lot of things that go into affecting our body mass index. It's not just isolated by itself. There's a lot of other variables that are interrelated with it. Okay, so there may be a validity to the model, but if the value of r squared is small, then we can only talk about the presence, the direction, and the magnitude of a correlation. Okay, so of a correlation or an association. Okay, so if we're just interested in the presence, direction, or magnitude, and a value of r squared, a small r squared, may be okay. But, there's a difference between having a practical effect and having a statistical effect. And so I give the example, if there's a diet and it turns out to be statistically significant at helping you lose weight, but the effect over 3 months on average is half a pound, then who of us is going to put ourselves through that diet regimen only to lose on average half a pound over 3 months? It's not practically efficient or good for a practical use, even though it may turn out to be statistically significant. Okay, so now we're going to turn to some R code, and so you can use R code from this. It is so you can't copy it here, but I will put a file in on Moodle so you can use this. Just make sure that when you're doing your projects and your homework that you take out the stuff that I've put in there as explanation and teaching, because you're not trying to teach when you turn in the homework. You're trying to present like you would to your boss or to your boss's boss or something. You're not going to be saying, okay, this could happen or that could happen. You just want to put in what's pertinent. So take out the things that you don't need from the file before you turn it in to me, please. Clean it up. Okay, so let's perform a hypothesis test for rho equals 0 versus rho not equal to 0 at alpha equals 0.05, and also let's compute a 95% confidence interval. So this very short statement does all of that. So the method is Pearson. That's the type of correlation coefficient that we've been talking about. There's different types of correlation coefficients. There's Pearson, Spearman, Kendall's tau. There's several. We're using Pearson. The alternative is what type of test it is. Since this is a not equals to, it's a two-sided. And I've included that we can change the confidence level. The default is 0.95, but maybe you get asked to do a 0.98 or something, so you need to know what to change in there. And here we're doing the correlation between the age and the log of the dry weight. Okay, so here's the output with the double pound signs. And so it tells you the data, it tells you the t-value, the degrees of freedom, and the p-value. Look how small this p-value is. This is an 8 with 13 zeros in front of it. 8399 with 13 zeros in front of it, that's pretty small. It also tells you nicely what the alternative hypothesis is, that the true correlation is not equal to 0. And that's based on the fact that we said two-sided. If we said greater, then it would say greater than 0. If we said lesser, it would say less than 0. And so here it tells us it's a 95% confidence interval. And so that's very nice. And then it also tells us what the correlation coefficient itself is. Okay. Now, here is how we would analyze that. So what we do is we look at the test statistic, and we say that it has 9 degrees of freedom, and that corresponds to a p-value here that's less than alpha, because alpha was equal to 0.05. Hence, we reject H naught. There does exist sufficient evidence to support the claim that the true correlation between age in days and the log base 10 of chick dry weight is different, because that's a not equal to, than 0. At a 95% confidence level, the test was performed using a random sample of size n equals 11. You need to do this when you turn in your homework. And then we can say that the 95% confidence interval for rho, not R, but for rho, is here. And I've put it to 4 decimal places because you need that. It would go to 1, and we don't like to put 1 for the upper limit here, unless it actually is. Okay, so, and this shows that our correlation, that 9992, let's say, it's inside this confidence interval. Okay, so that's why, so it's inside the confidence interval, of course, because it's in the middle, right? We used it to do that, but it's that close to 1. Okay, very, very close to 1. What if we want to test the hypothesis now that rho is equal to 0.75 against a one-sided alternative? Rho is greater than 0.75, and again at alpha equals 0.05. Well, we'd have to use the Fisher transformation because this value is not 0, and that's the only way we can do that. So I found this package DevTools, and I didn't spell it right. I think it's this way, that does all of the transformations for us and calculates a confidence interval. So I wrote this code for you so that you can just use it. They had all the tools, but they didn't put it together as nicely as core.test up above. So here is core CI, and so it rho in the confidence level equals, and I set that to 1 minus alpha 1, and that's a mistake. So I needed to make this 1 minus alpha 1 divided by 2. So I just see my error there, so we'll want to change that. I'll change it before I give it to you, but we'll now pretend like alpha equals 0.1 instead of 0.05. All right, so that's because that's the confidence levels that are going to be, our confidence intervals and tests that are going to be done. All right, so this gives us the confidence interval very nicely, okay? And so we see 0.273 all the way up to 0.931. That's a big range. And that's around saying that it's 0.75. Okay. So here's the code. You don't have to do anything. This is not the best written code, but it works. So if you have two-sided specified up here for the test direction, then it does that. We have greater than, or greater, and then you can see that the other that you could use is less. So there's less, and here's greater. And here's what the output looks like, okay? So yeah, I'm not going to go through the code line by line. You can do that if you're interested, but the key is you're going to use it. So here it gives us a t value of 3.402, our degrees of freedom, and the p-value is 0.0039, and based on this, we're going to reject H naught using an alpha of 0.05. So I've given you everything here you need to write the concluding statement like I've shown you up above. Okay, so that is it for this chapter. We did not talk in the code about how to compare two correlation coefficients. We'll do that later on without a straight line, where it's not a straight line, and it becomes a lot more important than right now. That really didn't fit very well with our straight line because we only have one variable, not 3. Okay, so don't forget to scan your lecture notes by midnight on the date listed in the course calendar. Be neat, because you're the one that has to read them. Update your formula sheet with some of the formulas we had here. If you have questions, come to virtual office hours. If you absolutely can't come to virtual office hours and it's urgent that you get an answer before the next office hours, by all means email me, but take a picture of what you've done and the problem. That way I can see what the problem is and what you've done, how you've approached it, and that'll help me help you. So take care, and we will see you next time.